executed, so that way no matter where you call your code, the C compiler will know, hey, this function exists somewhere else in the line of code. So that way the order of your execution or calling of functions doesn't affect anything. Yes? You don't always need to put the parameter name in the prototype. No, it's optional. I usually like to, just to keep things standardized, and so people, like, if they just see the function on its own, they get a slightly clearer idea of what's going on with it. But yeah, the name is optional in the prototype only. So now the next question says, given the function prototype above, fill in the function so that it finds the sum of the numbers from 0 to input inclusive. So what we're trying to do here essentially is if input is equal to 3, we essentially just do 0 plus 1 plus 2 plus 3. That's what we want our function to do. So let's start writing that. So I'm going to redeclare this function. So int find sum, we have an int input. So now that it's not a prototype, we actually want to fill it in. So our first step is, well, if we're going to be summing things over and over again, we're probably going to need some kind of looping structure, right? So I'm going to declare a counter. Generally, I is a common practice for this. Your counter can be called whatever you want. It's a variable name. So I would say int I. And we're also going to want to keep a total sum of everything. Yes? Oh, yeah, that was arbitrary. That was just an example, yes. So we're also going to need some kind of variable to hold the running sum of everything. So what I'm going to do is, instead of actually just declaring I, I'm also going to declare another variable called sum, and I'm going to start it equal at 0 because we're going to be adding on to it over and over again. So now I'm going to set up my loop. So I want it to loop essentially as many times as the value of input, right? Because this adding 0 to it won't really affect anything. Sum starts at 0. So I essentially want to loop it 3 times. I want to loop it for 1 plus 2 plus 3, or whatever the value of sum is. I just want to loop it 3 times, 4 times, whatever input is. So I'm going to set this up. So I'm going to say for I is equal to 0, I is less than input, I plus plus. So now all I really wanted to say is just sum plus equals I plus 1. So now the reason I'm doing I plus 1 here is because I started I at 0, and we don't really care about adding 0 to it. We just want to do 1 plus 2 plus 3 all the way up to our number. So we'll just do 1 plus 2 plus 3. Conversely, we could have set up this loop so it looks like this. For I equals 1, and then I is less than or equal to input, and then we can just say sum plus equals I, like that. And that might be a little bit more legible for other people reading the code, but it essentially produces the same output. And so this will find the sum of all the numbers up till 1. And remember, this function returns an integer, so we want to return sum at the end. Let me return sum at the end. Yes? If you made I less than or equal to input, you would go 1 extra time, because you're going from 0. You would be looping from 0 to whatever input is, like let's say 3. If you go from 0 to 3, it'll actually loop 4 times, which I guess if you're also adding 0, it wouldn't matter. But in this case, if you were adding anything else, you might do an extra addition that you wouldn't want to. So in this case, you could just say 0 less than or equal to input, just because we're adding 0 at the beginning, and it doesn't change the effect of the operation. But it's something to keep in mind. Yes?
When you increment I at the end of a for loop,
yes.
It doesn't matter in a for loop, right, if you do the implementation before, like plus plus I, or I plus plus in a for loop. But as for while and other loops, like while and for else, I believe they do. Like the condition of the placement of plus plus does matter.
Well, so for while loops, it might not matter depending on how you're incrementing it. But if you're looping in such a way that you want to increment a counter anyways, you'd probably be using a for loop. But for this case specifically, it doesn't matter. And it really kind of depends on what is like this I++ wrapped in anything. Like, are you calling a function with I++ or ++ I or something like that?
Okay. So in a for loop, it doesn't matter.
Yeah. So unfortunately, I've got to keep moving. I'm going to save some time for questions at the end while you guys are doing surveys. But for the most part, this is going to be like lecture style. So it's just going to be me solving the questions. So here's another code tracing, but with functions now. So it's just asking, what is the output of the following lines of code? So we're calling some functions. We've got a couple variable declarations. So we've got x is 12, y is 15, and then we've just got z. So here we're saying z is equal to molt y3. So molt ab just returns a times b. So it's just a function that multiplies the two numbers. So remember that when we call a function, and if we know its return, all that really happens when we call the function is that the function call itself is it just returns some value that has to line up with whatever the data type of this is. So molt returns a times b. We're going to assume here molt returns a times b as an integer, which means if molt returns an integer and z is an integer, this is fine. So this would just return y times 3, where y is our a and 3 is our b. So y times 3 is just y equals 15, so z is equal to 45. Now pow ab says here it returns a to the bth power, so we essentially get a to the b. So we have x equals pow 1, 2. We're going to assume, again, pow is returning an integer. Generally on an exam or something, a professor would be specific and say, hey, this function returns an integer, just in case, for example, if x was a float and you try to set it equal to the return of this function, those don't match up, so you would have some kind of compiler error. But here we're going to assume it returns an integer, so this is just saying x is equal to 1 squared, which is just 1. So x is now set to 1. And now we say z plus equals pow of y1 plus x. So first we evaluate this function call. So pow y1 is just 15 to the first power, 15 to the first power plus 1. So z plus equals 16. So z before was 45, so we're really just going to do 45 plus 16, which is equal to 61. So now when we print out here, we're doing x, y, and z. Well, x here was just 1. So we get that 1. Y was 15. It never got modified. So 15. And then z at the end was 61. And so that's the output of that. So now here, we're working with statically allocated arrays. So this is asking us to write a function that receives an integer array and an integer representing the size or length of that array, and it returns the amount of even numbers in that array. So we're essentially given some array, and it's got some integers in there, and we want to return the amount of even numbers. So here 2 and 4 are even, so we would just return the number 2. So they don't really give us a name or anything like that, so I'm just going to kind of come up with my own function. Generally, a professor would either ask or give you a name to call it, or they would just let you call it whatever you want. So if we're returning the amount of even numbers in the array, well, that's an integer, right? We're just counting up how many even numbers there are. So I can just say int, and I'll just call this function num evens. And it receives an integer array, so I'm going to say int arr. And it receives an integer representing the length, so int, or the size. I'm going to call it length. I'm going to move this 2. So let's move this up a little bit. All right, so we get this array, and we know its length, which means we can go through each array and figure out how many even numbers there are. Now, we know that the definition of an even number is that it's evenly divisible by 2, which means that if we have some n in this array, we want to check if n mod 2 is equal to 0, right? Because if n mod 2 is equal to 0, if that condition is true, that means our number is evenly divisible by 2. So since we're going to be going through an array, typically a way you go through each array is in some kind of loop because you have multiple elements. So you're going to be looping some set of code over and over again. So again, I'm going to set up my counter variable. And then I'm just going to say, I'm also going to create something that keeps track of how many evens I've got. So I'm going to say evens is equal to 0. So now the way I'll set this up is I'll say for I is equal to 0. We know the length, which means we're going to be visiting every single element, right? Because we got to track how many evens there are in this entire array. So I want to say I is less than length, and then I plus plus. Now in this case for this array, right? This array is 0, 1, 2, 3. This array has a length of 4, right? But since arrays are indexed starting at 0, we actually want to stop at 3. So that's why this is strictly less than length. If we said less than or equal to length, when we go to index our array, we would try and visit index 4, which doesn't exist. That would cause an error. So you want to say strictly less than length, and then I plus plus. And now in this loop, what I'm going to say is just if. Now I want to check the element at position I. Yes? It just has random integers, yeah. Yeah. So, so remember the way we check an element inside of an array with statically allocated arrays is just using bracket notation. We can just say if the array at position I mod 2. So here we're saying if the element in array at position I mod 2 is equal to 0, so if it's evenly divisible by 2, I'm just going to increment evens by 1. Evens plus plus. So now increment goes from 0 to 1. So in this case, I starts at 0. So for this array, array sub 0 is just equal to 1. So this condition isn't true, so nothing happens. Now array sub 1 is equal to 2. 2 mod 2 does in fact equal 0. So evens goes up by 1. 3 isn't true, so evens doesn't change, and 4 is true. So by the very end of this loop, give myself a little bit more room, we can just return evens. And that will give us how many even numbers there were in that array. Let me check how we're doing on time. Cool. So yeah, that's kind of just how we operate with arrays. Generally, if you're doing stuff with arrays and looking through them, you want some kind of loop to loop through like all the times you're accessing the different indices. Yes?
So if you have a printf statement in main, right? And
Okay.
you call num evens, it would return 2 evens at the end, right?
Yes.
Run function return evens.
Yes. So now here's a problem on two-dimensional arrays. So it says in main, so we're just going to be operating in main, write a program that creates a 4x4 two-dimensional array and populates it with random values between 1 and 100. Okay, so let's start off with main. So int main void. So here I'm using void just to specify that main isn't taking any parameters. So we want to create a 4x4 two-dimensional array. So remember the normal notation for a one-dimensional array is just int, say I call this ARR. We just use a single bracket. That creates a singular array of size 4. With a two-dimensional array, pretty much all we do is just add a second bracket. And that gives us our two-dimensional array. Now, this inner bracket, you can think of it as the rows. So if we have this grid, if we think of this grid as our two-dimensional array, this is a 3x3, but that's OK. Well, I can make it a 4x4. Do that. So this inner bracket keeps track of 0, 1, 2, 3. If you think of a two-dimensional array as an array of arrays, this inner bracket tells us what array are we looking at. This outer bracket tells us the columns, or what element are we looking at in that array. So for example, array sub 2, 3 is saying, okay, look at array 2 and go to position 3, and that's that position right there. So we've created this 4 by 4 array, so now we need to actually populate it with random values between 1 and 100. So since we're going to be looping through this two-dimensional array, we're actually going to need a nested for loop, right? Because we need to go through each of these arrays, but before we move on to the next array, we need to visit through every single spot in that and then increment this. So normally if we have two indices, we'll use I and j. I'll declare those on a different line right here. So now I can say for I, let me give myself a little bit more space actually. Yes, I was going to get to that. So one thing that I haven't done yet that is important for you guys to keep track of is that if we're going to use random values, we need to seed the random number generator, right? Because the random number generator is just an algorithm that has some initial input and then it just runs through some math to appear random. But we need to seed it first. We need to give it a starting point. So generally, if you're going to use the random number generator, you're going to want to call srand and time null. So we're going to need time.h. And I believe we'll also need the standard library. So here we were just assuming that the only thing included was like standard I/O. So now I've included the standard library. So now we have all the functions needed to run our random number generator. So now here, something we can typically do is just call srand on time null. So what this is doing is it's saying, okay, when we pass it time null, it's just giving us the exact second at that very moment, or how many seconds it's been since January 1st, 1970. So it's just some very large number. And then srand is using that number as a starting point for the random number generator. So since this number is always increasing, it's always changing, it's pretty random. It'll be random enough for our purposes here. So now we've seeded the random number generator. So now I can say for I is equal to 0. I is less than, we know this is a 4 by 4, so we can just say 4. We want to increment by 1. And now in here we'll also have another loop for j is equal to 0. J is less than 4. J plus plus. So this outer loop is going to be going row by row. This inner loop is going to be going column by column. So now in this inner loop, we just want to say array at position I, j is equal to, so now here we're going to call our random function. So if I were to just do rand like this, what rand returns is any valid integer within the range of acceptable integers. So we get a number from essentially negative 2 billion to positive 2 billion. And that doesn't fit our range of 1 in 100. So if you want to constrict the return to a certain range, generally the strategy is to use the modulus operator to your advantage, right? Because if the modulus operator is the remainder from division, that means the remainder can be only between 0 and whatever number you're doing the mod by. So for example, like anytime I mod something by 10, the only actual result of this operation can be 0 to 9. So if I want it between 1 and 100, my first step is I can just say rand mod 100. So rand mod 100, that can give me any number between 0 to 99, right? So if I want this between 1 and 100, I can just take that range of 0 to 99 and shift it up by 1. So in order to do that, I can just say take the result of this and just add 1. So now we're in the range of 1 to 100. And it doesn't ask us to do anything else with the program. Ideally, you'd want to print this or something like that, but the program just ends up populating it with random values. So we're done with this for now. So let's move on to strings and string functions. So we've got a couple conceptual questions here. So this first one asks, what would be the array elements of a string that contains the word hello? Now remember, a string is just an array of characters, but with some special properties. So here for hello, we would have something like this. So we would have an H, an E, an L, and an O. Those L's are a little. An L, and an O. But not just that, if a string is to be properly formatted in C, what we also want is the null terminator, so this \0. So the array at the end would look like this. We have H, we have an H, E, L, O, and then the null terminator. So what the null terminator does is it tells C, hey, this is the end of this string. And it's used in a lot of important string functions, like this next one we're going to cover, the string copy function. But yeah, so the answer to this problem is just H, E, L, O, and then the null terminator. Every string should end with the null terminator. And if it doesn't, you're going to have some problems when you're trying to call string functions on it. And just having the null terminator makes it really easy for you to know when the end of the string is, and when for C to know when the end of the string is. So when using the string copy function, which argument is the destination and which is the source? Now, if you guys remember, the string copy function just copies the contents of one string into another. So if we have like one string called hello and another string that's empty, if we call the string copy function, we can put the characters for the word hello into that empty string, and now both of them say hello. So the format of the string copy is strcpy, so that's the string copy function. Then the first parameter is the destination, and the second parameter is the source. So that means the contents of source are copied into destination. So if the second string is hello and the first one is like goodbye, we overwrite goodbye with hello and a null terminator. String copy adds a null terminator for you. Most of the string functions account for the fact that there needs to be a null terminator, so you don't have to worry about putting the null terminator yourself. Speaking of the null terminator, this next one just asks, does the string length function account for the null terminator? So if I had this hello string, let's just say I have this saved in a string called str, we would say something like string length would be strlen str. So this would actually, the way it works, and this is one of the first ways we see the use of the null terminator, is it goes element by element, and for every character it sees, it just adds 1 to some counter, and then it stops when it sees a null terminator. So it would go 1, 2, 3, 4, 5, and then stop. So it actually does not account for the null terminator. So you need to remember whenever you're doing some memory allocation or anything like that, you need to add an extra space for that null terminator. So the answer to this question is no. Yes? I'm sorry? I think it takes up the same amount as a character, so 1 byte, but I'm not entirely sure. So this is a true or false question. strcat string 1, string 2 returns the string str2, str1. So this isn't literally the string str2, str1, but it means like whatever str2 is and then whatever str1 is, those strings put together. So this is actually false. What strcat does is it concatenates this first string with the second string. So if str1 equals, let's just say hi, and str2 is bye, what this returns is hi, bye like that, not bye hi as this is implying. So the answer to this is false. And this last conceptual question is asking, what does the string compare function return if two strings are lexicographically equivalent? So what does it mean for two strings to be lexicographically equivalent? That just means essentially they're the same string. All of their values for all of their characters are the same in the same order. So if they are the same, it should return 0. If they're different, I believe if the first number, or if the first string is lexicographically greater, so it has maybe a higher value for the first character or second character, it returns a positive number. Otherwise, if the second one is greater, it returns a negative number. But yeah, if two strings are the same, the string compare function should return 0. So now we have this problem. So fill in the following function that's given a single string. If the string contains every letter of the alphabet, return 1. Otherwise, return 0. So notice here we're not given the length of that string. We don't know how long our string is. However, the neat thing about strings, given that, assuming that it's properly formatted, is that null terminator we can use in these kinds of string problems. So how do we approach this? How do we figure out if the string contains every letter of the alphabet? Well, what I'm going to do is I'm going to use an array to keep track of the letters that have shown up. So what I'm going to use is essentially something called a frequency array. So it's an array of frequencies of different things that appear. So this array is going to have 26 cells, one for each letter of the alphabet, starting at 0 up to 25. What I'm going to do is I'm going to take each character in str, and whatever it is, I'm going to use that letter as an index for this array, and I'm going to increment the value in it. So originally, all of these will be set to 0. So 1, 2, 3, 4, 5. So each of these numbers is representing a letter, right? So this 0 is going to be A, this is going to be B, this is going to be C, D, E, F, G, and so on. We're going to assume for this problem that all the characters in this string are going to be lowercase letters. We could modify it so that it works with uppercase letters as well, and I'll show you guys how to do that. For now, we're just going to assume that it's lowercase letters. So first of all, to start off, again, we're going to be looping through since we're dealing with a lot of strings. So I'm going to want an I. Now, additionally, we need to create our array of frequencies. So, and we want it to start off at 0. So I'm going to say int, I'm going to call this letter frequencies, or letter FREQ. And we want it of size 26. And now there's two ways we could populate this with all zeros. So one way is to just write a loop that goes through 26 times and it populates every cell with 0. Or another shorthand in C for this. This specifically only works with the integer 0, is to do that. That starts off every element in the array equal to 0. It only works with 0, and I believe this only works with integer arrays. So like I said, the alternative to this is just create a for loop. For I equals 0, I is less than 26. Each element, letter frequency C sub I equals 0. That would be another way to do that. So I'm going to set all those elements to 0. So now we have this array initialized to the side. So now the idea is to do something like this. So if our input string is something like the word ball, we would see this letter B. Well, they're supposed to be all lowercase, but we would see this letter B, and we would say, OK, let me go to this array here at position B. And we've seen a B, so I'm going to increment this to 1. Now we move on to the next letter. I see this letter A, move to this array at A, increment it to 1, and then repeat that for L. Then what we need to do is it needs to contain every letter of the alphabet. So the last thing we need to do is loop through this array to see if everything is at least greater than 0. And if they are, that means great. It contained every letter of the alphabet. Otherwise, it did not, and we would return 0. So our first step is going to be take our string and figure out how we're going to traverse through it. So I'm going to say for I is equal to 0. So here we don't know how long the string is, but we're assuming it's a properly formatted string, which means what we can do is we can just check, we can just keep going as long as at position I inside of the string, we don't have a null terminator. Because we can't really check the null terminator as a letter, right? It's not an actual letter. So I can just say keep looping as long as str at position I does not equal the null terminator. Now remember, for equality operators, we have double equals for seeing if they're the same, not equals, this exclamation mark equals to see if they're different. So keep looping as long as the str sub I does not equal the null terminator. So the null terminator is a character, so we use single quotes. and then just increment I. So now, here's how we're going to traverse through this loop. So I have to figure out a way to get from the letter A to position 0 in this frequency array, right? Well, the neat thing about characters in C is that they are all stored as ASCII, which means ASCII is a standard for mapping letters to integers, essentially. So technically, every character in C is just some integer from 0 to 255. And because of this fact, we can do some arithmetic on characters like math. So yes?
So is it like, since it's in ASCII, I think lowercase a is 97 in ASCII,
Yes.
right? And then uppercase is something like 60 something?
Yes.
How does that work? Like, what is the connection between letters and ASCII? Is it just
I believe like the reason they are the way that they are is the first set of ASCII characters, like 0 through like 15, are specially reserved for like end of file and other kinds of flags that normally you wouldn't use in normal ASCII. From then on, I think it's just kind of arbitrary the way they assigned it. I'm not entirely sure. I don't think it doesn't make a difference for like the purposes of this problem, but yeah, I'm not entirely sure about that. But we are actually going to use that property of the fact that lowercase a is 97 to benefit us. So what we need to do is we want to index this array, right? Because we're going to be going through this letter array, and we want to increment it. So how do I want to increment it? Well, I need to look at this letter and figure out, given this letter, what index of freq array I'm going to look at. Well, how do we do that? We can take our character. So let's say we have a letter B. So like he said, if A is 97, that means B is 98, right? Well, we need 98 to somehow map to 1. Well, since we know everything starts from A and then on, we have this character B. If we subtract A, that means that gives us 98 minus 97, which equals 1. And that's how we're going to get our indices. We're just going to take whatever letter we find, and we're going to subtract the character A from it. And that will give us these indices down here. So first we got to do str at position I minus the character A. So that's given us what index to look at, right? But remember, this entire thing is just an index for the letter frequency array. So now we actually need to put that as an index. So we would wrap that in here and say, so the letter frequency at position, whatever the current character is minus A, and then we can just increment it like that. So what we've done is we figured out, using this operation, we figured out what index we're looking at, and then we're actually indexing it and incrementing it. And remember, they're all 0, so it'll just go up by 1 every single time. So now that we've done that, this should loop through every single letter in str. So now what we need to do is just loop through this letter frequency array and make sure everything is 1, or everything is not 0, essentially. So we're going to do another loop, and I'm going to reset I to 0. And I know that this only has 26 letters in it, or 26 indices. So I'm going to say for I is less than 26, I plus plus. Now what we can do is we can just check if there's a 0 in here. That means there was some letter that wasn't. There was some letter that just wasn't in that word. So we know that the condition isn't true. So we want to return 0. So we can just say if letter frequency at position I is equal to 0, well, that means it's false, so we would just immediately return 0. Just immediately leave this function, we know it's not true. So now, if we get down under this curly brace, that means we never return 0. If we never returned 0 up there, that means there must have been a 1 in every single cell of that frequency array. So that means this is actually true. So now we can return 1. And that is the whole problem. So, oh, that's correct. It is a void function. This should actually be an integer function. My bad. So let's change that to int. So now we would be correct to return 0 and 1. Before, we can't really return anything from a void function. So that's some stuff working with strings and indexing strings, figuring out how to get characters from them, and also operating with a null terminator. So now let's do some stuff with file, input, and output. Let me see how we're doing on time. Cool. So now we're at file input and output. So this is asking us to write a program that scans in all of the integers from a file named input.txt, and the file is of the following format. The first line contains an integer, n, and it'll be followed by n integers. So print out the amount of numbers that are divisible by n. So this is kind of similar to our previous problem where we wanted to see if all the how many elements in the array are divided by 2. Now we're just given a file, and it tells us how many numbers are in that file, and whatever that number told us of how many numbers are in there, we want to see how many numbers are divisible by that. So for example, we have our input.txt here. So I'm going to zoom in on that a tiny bit. Oh. Let me just make it larger. So we have input.txt here. And it says the first line contains an integer n, so let's say 4, for example. And it's followed by 4 integers. So let's say these integers are just 16, 12, 1, 3. So we want to see how many of these numbers are divisible by 4. Well, what we would do is we would read through this file. We get the number 4, so we know there's 4 integers after it. And we would say, OK, this 16, that's divisible by 4. That 12 is divisible by 4. 1 is not divisible by 4, and 3 is not divisible by 4. So we would just print out the number 2 to say that there are 2 integers in this file divisible by 4. So to start off, usually when we're working with file I/O, we're going to need some kind of file pointer. So remember, a file pointer is just a special pointer that knows the location of a file in memory. So we have file asterisk, and I'm just going to call this IFP. So also, since we're going to be scanning through a bunch of integers, we're going to be doing a lot of scans. I'm also going to declare an integer. I'm going to get rid of this curly brace. We're going to need more space than that. I'm going to create an integer I. And we're also counting the numbers that are divisible by n. So, well, first of all, the first line contains an integer n. So this is going to tell us how many times we're going to have to scan these numbers. So I'm also going to say none for this first number. And we also want to count of how many numbers are divisible by n. So I'll just call it divisible. And I'm going to start that at 0. So now what we want to do is we want to open the file. So the way you open a file pointer, or the way you open a file and set a file pointer equal to that is you use the fopen function. So you call the fopen function on that file pointer. So you say ifp equals fopen. So the fopen function returns a file pointer. It returns an address, a memory address to a file in memory. IFP wants one, so we're going to give it to it. And it takes 2 parameters. It takes the name of the file and the mode we want to open it in. So here, if you're in the same directory, if your code is in the same directory as the file you're trying to open, you can just give it the file name. This is essentially called a relative path. It just assumes it's in the same directory. So here we're going to assume input.txt is in the same directory. If it weren't, you would have to give it the full file path. So like for Windows, it'd be like C://home all the way to, yes?
Don't you need like 2 colons if you get the full file path in C? Or if you're using, I think Windows, you have to use 2 colons in Linux as well.
Yeah, I think in Windows you have to use 2, in Linux you don't. Or it's the other way around.
I think, well, in Windows, I'm pretty sure it's 2 because I've been having to use 2.
Okay. Yeah. So if you're giving it the actual file path, the absolute file path, then yeah, when you're formatting it for Windows, you'll need the 2 colons. Generally, for problems like on exams and stuff like that, you'll just assume it's in the same directory. So we know our file is called input.txt, so I'm just going to say that. Now, in this case, we're not modifying the contents of the file, so we're going to open it in read mode, which is R. If we wanted to write to the file, we could open it in write mode, which is W. And to do both, you can do like RW or RW+. That will open it in a way that you can both read from and write to that file. So all we want to do is read from that file. So now we want to take some input from that file. Now for normal input, like input from a terminal or the command line, we use the scanf function, right? And the scanf function just requires we give it a conversion code to say what we're scanning in, and the address of some variable to say where we're putting it. The file equivalents are very similar. We would just say fscanf, and the only additional thing we need to give it is what file pointer are we looking at? What file are we actually scanning an input from? So here I would just say fscanf keep breaking these. So fscanf, and the first parameter is the file pointer we're looking at, so IFP. The second parameter is what kind of data are we reading in? Well, we're reading in integers, right? So this is going to be %d. And now the last thing is you need to give it some address to put it in. Well, here I have this variable num for keeping track of how many numbers there are. So I'm just going to say the address of num. So now it's putting that number into the address of num. And now remember, normal scanf is just pretty much this part. We would do something like that. If we were writing to the file, we would use file IO's equivalent of printf, which is just fprintf. It's the same as normal printf, except now we also give it the file pointer. In this case, we don't need to write to the file, so we're not going to use fprintf. Now, the next step is we know how many numbers there are now, right? Because that's what they told us. This first number tells us how many numbers follow it. So what I can do is that lets me set up my loop. That's going to tell me how many numbers am I going to scan in and see if it's divisible by num. So I'm going to start my loop. I'm going to say for I is equal to 0. We know that whatever num is, there are num amount of numbers. So I is less than num, and then I plus plus. So now I need a temporary place to hold each of these numbers to check to see is it divisible by num. So what I'm going to do is I'm actually going to add a new variable up here to my integers. And I'm just going to call it maybe like current to say this is the current number I'm looking at. And it doesn't need an initial value because I'm just going to be populating it as I go along. So let's say I'm going to do something like this. I'll just say fscanf. I want to scan in these values into current. So fscanf IFP, we want to scan in an integer into the address of current. So now we've scanned in this first integer, assuming I is equal to 0. We've scanned in this first integer into current. So now we need to check, is it divisible by num? So we would say if current mod num is equal to 0. So if current mod num is equal to 0, that means that it's evenly divisible by num. Then we can just say we have this divisible counter that's just counting how many things are divisible by num. We'll just say divisible plus plus. And this will keep looping for everything inside of that file. And then at the very end, we're just printing out the amount of numbers that are divisible by n. Well, that's held inside this variable. So I will just say printf. They don't specify what to say in that printf other than the number, so I'm just going to print out %d, maybe a new line for formatting, and then I'll give it divisible. And now we've printed out how many numbers are divisible by n, yes. In the back first, sorry. Yes, fscanf knows to go down, essentially. It'll skip the new lines, because then every time you go down a line, there's an invisible new line character. Since we're scanning in only integers, it'll just ignore that and go down a line. It would be the same. This problem would essentially be the same even if we had the numbers all in a line. Yeah, spaced out, it would work the same way. Yes. Yeah. Normally fscanf is separated by white space. You can actually change what denotes different numbers. You can make it like a comma or something like that. You can change what's called the delimiter, which is what says, hey, fscanf, ignore white spaces. Say the next number starts at the next white space. You can say, now it starts after a comma, or something like that. What was your question real quick?
It might be a bad question, but are you going through the whole file, right?
Yes.
You want to skip the first number, right?
Yes.
So do you skip the first number? Or?
Yeah, well, what happens if when you call fscanf, it moves the file pointer after you call it. So the file pointer starts at the beginning of the file, and so this 4 is the beginning of the file. Once we've called it, the file pointer is now starting at 16. So it skips that first number. And we don't really care about that first number because we know it's divisible by itself. We're just looking for the rest of the numbers afterwards. All right, so now we're moving on to pointers. So now, as you remember, pointers are just variables that hold addresses to something else in memory. So For example, if I've declared an integer, it can have the address of that integer, and we always have a reference to where that integer is in memory. Pointers are super useful for needing to access variables in some other function where we might not have created it yet. Or we've already created it, but it's in a different function where it wasn't created. So this first question is asking, what is wrong with the following lines of code? How can it be fixed? So let's go through these lines and see what's going on. So we have int x equals 15. Nothing looks wrong there. There's a semicolon, single equal sign, everything's OK. Int star p is equal to the address of x. Well, the way we declare an integer pointer is we say int star, and then whatever we're calling it. So here it's called p, and it's equal to the address of x. Well, like I said, pointers hold values that are just addresses in memory. If we're giving it the address of x, that's exactly what it wants, so that's fine. Now we say star p is equal to 9. Now remember, after we've declared the variable, when we put the star next to the pointer, what we're saying is we're dereferencing that variable. So whatever p was pointing to, so here p is pointing to x, we're saying go to x, so essentially star p is now x, and set it equal to 9. So if this is like a little map of our memory, we have x, and it's 15. Oop, that's a bad 15. And then we have p, and it just holds the address of x. What we're saying when we're dereferencing it there is we're just saying go to x, and whatever's in x, set it equal to 9. So now it's equal to 9. So now here we're saying printf %d/n p. Well, %d is a conversion code for an integer, right? Now p is not an integer. P itself just has a memory address. So these are conflicting types. This is asking for an integer. We're giving it an address. So how can it be fixed? So one way might be to just change this to a %p. %p is the conversion code we need for printing out pointers. So this would print out that memory address just fine. Alternatively, if we wanted to actually print out an integer value, what we could do is keep this as an integer conversion code and just dereference p. So when we dereference p, we now get the actual number stored in what it was pointing to. So those are two ways that that can be fixed. Yes? Can you repeat that? It actually, if it does that, I guess it would try and convert it. But I think in this case, since p isn't an integer, printf will actually, it won't try and convert it to an integer. It'll just yell. It'll say like, hey, you can't do that. If we said %p, it'll print it out in a hexadecimal, and we could change that hexadecimal to an integer. So now this next question is saying, fill in the blanks with the proper data types that each variable should have. So here we have a bunch of variable declarations. We don't know what they are. We got to use these lines of code to figure out what they are. So this first line, it says r is equal to the address of c. Well, if r is holding an address, that implies r is a pointer of some kind. But we don't know what c is. We don't know if c is a double. We don't know if c is a float. We don't know if c itself is a pointer. So we have to move on. Here we have a equals r. If we're assuming all of the lines of code are valid, that means whatever r is, a also is. But again, we don't know what r is yet. Here we have star r is equal to 17. So we're dereferencing r and setting it equal to 17. If this line of code is valid, that means that whatever r is pointing to has to be an integer if we're assigning an integer to it. So that tells us right there, we know that r itself is an integer pointer. So we would say int star r. If r is equal to the address of c, and we know r is an integer pointer, and r is pointing to c, then we know c must be an integer. And we also know that a was equal to r, so that means whatever r is, a is. So we have int star a. So we know r is a pointer, a is a pointer, and c is an integer. So now we dereference h, and it's equal to a. So we dereference h, so h is some address over here, right? We dereference h and set it equal to a. So whatever h was pointing to, we're setting it to an address, which means if a is a pointer and h is pointing to something that's a pointer, then that means h has to be a pointer to a pointer, right? So if we draw our little memory map again, a is some pointer. It holds the address of, it's also holding the address of c in this case. when you dereference h, whatever it's pointing to is also a pointer. So we're setting it equal to the address of c in this line, in this line. So that means h has to be pointing to a pointer if whatever it's pointing to is equal to a. So these things have the same data type. So if a is a pointer and the thing h is pointing to is a pointer, this means it needs the address of whatever this is. So it needs the address of a pointer, thus implying that it's a double pointer. So we know we have int star star h. So h is a pointer to a pointer. Now this last one, I is equal to the address of h. That means I holds h's address. So if I holds h's address and h is a pointer to a pointer, then that means I is a pointer to a pointer to a pointer. So I is a triple pointer. So it's star, star, star. And that can keep going as long as we want. We can have a pointer to a pointer to a pointer to a pointer. Generally, most of the time you only see like a pointer to a pointer. I'm not entirely sure. I've never really tried out to see how many times I can go. Yeah, I'm not entirely sure how many you can go, but it is like valid to keep going essentially. So now this next question is asking us, how would we set the element at position 3 of an array called array, I'm not very creative with my array names, to be equal to 7 using pointer notation? Well, if you think of an array, right, an array, the way an array really works is just in memory, we have this variable called array, and it just holds a pointer, some memory address, that points to the beginning of this array, right? So the name array is just pointing to the beginning of this array. So if we dereference array, if we just say star array, well, what we're saying is go to what array is pointing to. Well, that's just this first cell. So star array is the same thing as array sub 0, right? All we're saying is just go right to the thing array is pointing at. Yes? Oh, I'm sorry. Let's see. I'll do this. I'll do it like that. So star array is equal to array sub 0. So now, if we want this next memory address, all of these memory addresses in an array, they're contiguous, right? They're all right next to each other. So how do we set something equal to like array sub 1? Well, if we know the addresses are contiguous, that means that we can use something called pointer arithmetic to just say, okay, well, if array is a memory address, array plus 1 is the memory address next to it. So star array plus 1 is the same thing as array element 1. So memory addresses aren't actually different by 1. What happens is if you're operating with pointers, C does the actual math for you. So it dereferences array, figures out whatever the memory address is, and adds 1 memory address, not 1 like just the integer 1. So it'll just go 1 integer over, essentially. So if we want to set element position 3 of this array called array to be equal to 7, well, first we have to access it using pointer notation. So I would say star array plus 3. So that's the position 3 in the array. And we just want to say equals 7. We're on time. Cool. Now, pass by reference functions. So here we're going to fill in the function that's given 2 pointers as parameters and swaps their values. This is a swap function, a very common example of pass by reference functions you see. So at the end of this, we want whatever x is pointing to be whatever y is pointing to, and whatever y is pointing to be equal to whatever x is pointing to. So people who might not have seen this problem before might think, okay, well, let me just say that star x is equal to star y, and then star y is equal to star x. Now, the problem with this is, let's say star x was equal to 5, and star y was equal to 7. Well, what's happening after these operations? Well, we're saying star x is equal to star y, so we're saying this 5 is now changing to a 7, so star x equals 7. And then we're saying star y is equal to star x. Well, we just changed star x to 7, which means all we're saying is just set star y also equal to 7 again, which didn't really swap our values, it just made them the same. So the way we get around this problem is to introduce a temporary variable that's going to hold the values of one of our variables. So that way when we go to do the final swap, it'll just, that temporary variable has the original value of whatever we're swapping. So I'm just going to call this integer old. So this is going to hold old, and it's just going to hold the old value of one of these variables. So I'm going to say that old is equal to not int, my bad. Old is going to be equal to, we're going to dereference x, so whatever value x was pointing to. Now we want to overwrite x, so we're going to say x is equal to whatever the value is y is pointing to. Now what we want to do is, we've just overwritten x, but old still knows what x's old value was, so we can say star y is equal to old. Now, I didn't have to dereference old, I didn't have to add that star, because old itself is not a pointer, it's just an integer. And star x there, when we dereference it, x is pointing to an integer, which means that old and star x are the same data type. So now we want to call the function from the previous question so that the values of a and b are swapped. So we have a here and b here. If I just call swap a and b, we have a mismatch of data types, right? First of all, a and b are integers. The swap function up here is, it needs integer pointers as arguments. Now, remember, integer pointers just hold addresses. So really what it's asking for is it needs addresses. So the way you would call a function is I would just give it the address of a and the address of b like that. Alternatively, I could have created two pointers that are pointing to numbers and pass the pointers themselves in. But in this case, I just have two integers that I'm working with, so I'm just going to pass their addresses. And now here, we're asking, this is another code tracing question, except now we're dealing with pass by reference functions. So it's saying, what is the output of the following program? So we have this function foo here. It takes two integer pointers and does some arithmetic on it. And then we have main, which initializes some variables and passes them to foo. So we have x is equal to 12, y is equal to 4, z is equal to 3. So now we're saying y is equal to return from calling foo on the address of x and the address of z. So this means that a is equal to the address of x and b is equal to the address of z. So that means that star a is equal to whatever x's value is, 12, and star b is equal to z's value, 3. So now we've got star a and star b. We can start doing this arithmetic. So now we're saying star a is equal to 2 plus star a minus b. So 2 plus star a, well, it's 12. And 12 minus 3 is 9. So we're saying star a is equal to 9. So star a equals 9. Oh, I'm sorry. Did I say, sorry. Yeah, 12 minus, no, 12 minus. Oh, yes, I'm sorry. 2 plus 12 is 14. 14 minus 3 is 11. Thank you. That should be 11. So we have 11 there. And now we're saying star b is equal to star b plus star a. Well, star b is 3, and we just changed star a to be 11. So 11 plus 3, we're adding that 3 back essentially to a different variable. Star b is now equal to 14. So now we would print f. A is equal to %d, b is equal to %d, and then we're dereferencing a and b. So this will print out a is equal to 11, b is equal to 14. Now we return 2 plus star b, so we dereference b and return 2 plus that. So here we're going to return 16. So we return 16, so now this line sets y to be equal to 16. So you have y is equal to 16, and then this just prints out x equals y equals z equals. So x is equal to 11, right? Because we were modifying x on the memory level back in the function. Y is equal to that 16, and z is equal to 14 because we were also modifying it in the other function. And so now we've worked with some pointers and done some functions with those. So now we've got dynamic memory allocation. So this first question is just asking us, what are the differences between the malloc function and the calloc function? Now remember, the malloc function, you call it on a pointer. It allocates some memory for you and returns the address of that memory. So we would say something like int star p equals malloc. And what malloc needs as an argument is a size in bytes. It needs to know how many bytes you want to set aside. Well, if you don't know the amount of bytes you're dealing with, for example, if you don't know how many bytes an integer is, you just call the size of operator, and let's say int, and it just tells you how many bytes that is. Yes? So in C, you actually don't have to typecast it. Malloc does return a void pointer, but C will just deal with that for you. In C++, it's required for you to typecast it. But in C, it is not. So now here, if we want, for example, 5 integers, well, this size of tells us how big a single integer is. So now we would just multiply this by 5. And now we've allocated 5 integers. Now the calloc function, if we change this, its arguments are a little bit different. The way the calloc function works is the first thing we give it is how many of that data type we want. So if we want 5 integers here, we say 5, and then we give it size of int. So that's one difference right there, is just kind of like its parameters, or arguments essentially. Whereas malloc only needs 1, calloc requires 2. Another difference is whatever memory you allocate, calloc zeroes it out. So if you're creating an array, like for example here I'm creating an array of size 5, calloc creates an array of size 5 with all zeros in it. Whereas malloc, the memory would be uninitialized. It would just be garbage values, whatever's currently in memory at that spot. So to answer the question, there are more in-depth differences between malloc and calloc, but for the purposes of this course, you don't really need to know them. They're much more in-depth operating system differences. Yes?
When I use malloc, I use the typecasting,
Mm-hmm.
but the amounts of whatever data type, like multiplied by the size of whatever.
Yeah.
It still works. Am I doing it wrong? Or?
No, there's nothing wrong with inside the parameters. If you do size of int and then times 5 or 5 times size of int, it doesn't really matter. With casting, it's a little bit different because in C, casting it, what that might do is suppress some errors that C gives you. So sometimes it's a good idea to not cast it, so that way if something were to go wrong, C would actually give you an error first. But it's not, I wouldn't say it's necessarily wrong to cast it, but it might hide some errors that would be useful. Yes? So as we'll see here in this problem, essentially the whole purpose of dynamic memory allocation is we want to allocate space for something that we don't know as we're writing the code. Like if we're taking in, like if we're writing something that takes in a text file and finds certain words, we don't know how big that text file is, right? We can't just say, oh, hey, create this integer of size 100, because we don't know how much is big, how big that file is. We could just create some huge array, but that's a waste of space. The good thing with dynamic memory allocation is we can basically cut down on as much space and create things as we go. So you can create like a number and then statically allocate array with like a variable in it. That's called a variable length array. Those were only added recently, as of like C99 or something. That's not backwards compatible. Another thing is sometimes its behavior is undefined, so it's usually a good idea. Come on. It's usually a good idea to just stick with dynamic memory allocation either way, since it has more defined behavior. Yes. Yes. So to answer the question, we would just say something like calloc zeros out memory and requires 2 parameters. Now, this next question says, fill in the following main function so that you ask the user to input an integer and then use that integer to allocate an integer array of that size and populate the array with values that are the negative of their index. So we're given like a number 4, and we take that number and we want to use dynamic memory allocation to create an array of size 4. And then what we would do is we want to put the negative of their index inside. So we have index 0, 1, 2, 3. Well, negative 0 is just 0, so we would have a 0. Then we would have a negative 1 in here, negative 2 in here, negative 3 in there. So first, we're going to need some kind of counter, because we're going to be looping through an array. We need to know how large the array is, so I'm going to say length. And that might be all we need for this problem. So I'm going to first, we need to ask the user to input an integer, and then use that integer. So ideally, we'd say printf, please enter an integer, something like that. For this problem, I'm just going to immediately scan. So I'm going to say scanf, and I want to scan in, it's an integer, so %d, and I'm going to save that to length. So I've saved this to length. So now I know how big of an array I should make. So this is going to be an array of integers, so I'm also going to have this int. If we're going to use dynamic memory allocation, we need to actually use call malloc on a pointer, right? And it's going to point to the beginning of that integer, or that integer array. Int pointer arr, and I'm going to initialize it to null. That's generally a safe thing to do, is just start it at null. So if you try and access it later, you just get an error that it's null. If you try and access garbage data, it might still run, and that might be a problem because that's undefined behavior. You don't know what's going to happen. So at least with null, you'll get some kind of error, and you'll know what happened. So now that we know the length, we can actually allocate memory for it. So now we can say arr equals malloc size of int times length tells us how long it should be, so length. So now we've allocated our memory. So now the next step is to populate it with the negative of their index. So we're going to start with for I is equal to 0, I is less than length. Remember, the final index of an array is just going to be however big it is, minus 1. And then I++. So we're going to increment from the beginning of the array. And we can just say now, even though it's a pointer, since it's a pointer to multiple locations, we can use array notation. We don't have to do the whole dereferencing and pointer notation stuff. So I'll just say array at position I is equal to, now how do we get negatives, right? I can't just say like negative I, that doesn't exactly work in C. Well, one thing I could do here to get negatives is I could just say 0 minus whatever I is. That would give us a negative number. So I'll just do 0 minus I. You could also do negative 1 times I. Either way works. I don't think there's actually any difference in the, oh, but then how would you get the negative 1? Because you can't just say like negative 1. Oh, I guess for integers you can. Yeah, you could do negative 1 times I, but you can't just say negative I. Sorry, yeah, you can use the negative for constants. So you could just say negative 1 times I or 0 minus I. Either way you want to solve that problem. As far as like computation is concerned, they're basically the same speed, so neither one would matter. And now we've essentially finished the problem, right? We've populated this array with values that are the negative of their index. So now here is a problem with a mix of some file input-output and dynamic memory allocation. So this is saying you are given a file called words.txt that contains an integer n, followed by n lines that contain 1 string each. Allocate a 2-dimensional character array that contains exactly n strings, and where each row of the array is allocated memory that is exactly equal to the size of that string. So we want to use as little extra space as possible. We want that array to be exactly as much memory as we need, not a little bit more. So we know the file is called words.txt, so let's create a file pointer. Remember, the file pointer has to be in all caps. I might not have done that in the problem before. So file pointer ifp, and I'm just going to fopen it on the same line. Fopen words.txt, and again, this is just in read mode. Generally, when you're dealing with file pointer stuff, you want to make sure fopen worked afterwards. So it's usually a good idea to check if IFP is null or not. Because if IFP is still null, that means that the memory wasn't allocated. Yes?
When we use malloc, do you have to use the free and then like free to pointer?
Oh, yes, thank you. That is something that I forgot to mention. When you are using memory allocation, that memory is just that memory you've allocated is just floating around in memory until you free it. If you forget to free it, like we did here, you're going to get something called a memory leak, where when the program ends, you had some reference to memory that the program was setting aside that you no longer have anymore, and it's just kind of floating around in memory. So you want to make sure that at the very end, so here we would return 0 at the end of main, we would free it. So we would free ARR. So now we've returned that memory back to the operating system. Also with file pointers, similar to freeing them, if you've fopened a file pointer, you also want to fclose it. It does the same thing. It's essentially freeing up the memory that that file pointer was pointing to. So we've fopened this file pointer. So we're also going to need a two-dimensional. So it's going to be 0 dot 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 to largest num. And I'm just going to keep a count of how many times each number 0 appears, or 1 appears, or 2 appears. So all of these are going to be initialized to 0. So I'm going to go ahead and create a, I'm going to need something to loop. Well, actually, in this case, it's not going to be an I. So I'm going to need to create this array. So I'm just going to call this frequency, or freq for frequencies. And I'm going to say sub size largest num. And remember, since we're initializing this to 0, we can just use this trick instead of having to do it in a loop. So now it's all set to 0. So we know the head of the linked list. Generally, it's not a good idea to overwrite the head. So I'm going to create a temporary variable that's equal to the head so that it doesn't change. So I'm going to say node, and head is a pointer, so I want star temp to be a pointer, equals the head. So if we have head is some variable that all it does is it just points to that node over there. I'm creating another variable called temp that is now also pointing to that node. What we're going to do is we're just going to have temp point this to this variable, look at the number, and then increment this array, and then point to this variable, look at the number, increment that array, and so on and so forth. So how do we know when we're done? Well, we know we're done if we get to null, right? Because as soon as temp points to that null, that means we've gotten off the end of the linked list, we're done. So I can just say while temp is not equal to null, here's what I want to do. I just want to say, I want to use the number inside of this node. So like if this is 3, I want to use that as an index for this array. So 0, 1, 2, 3, and then just increment it. So if that's a 3 there, I would change this from 0 to 1, right? And then if there's like a 2 here, I would change this from 0 to 1. If there's like a 15 here, I would go to 15 and change that from 0 to 1. So I'm using the numbers inside of the linked lists as indices for my frequency array. So I'm going to say frequency sub. Now temp is a pointer to a node, and this node struct has data, right? So I can say temp. Remember, temp is pointing to this node. It isn't actually that node. So that means temp, if I want to access the data of that node, I have to dereference temp and then access the data. So temp arrow data plus plus. So what this is doing is it's saying, OK, go into what temp is pointing to, access the data, access this number 3, use that as an index for the frequency array, and then increment it by 1. So now we've incremented that, and that's pretty much all we have to do. The next step actually in that while loop is now we need to move temp over. Well, how do we move temp over? Well, we see that the struct has a next pointer. It points to the next thing. So we can just say temp is equal to this node has a next pointer, so we just need to access it from temp. So we can say temp arrow next. And now temp goes from pointing to this thing to pointing to that thing. And that'll move all the way down the list until we hit null. Now that we've done that, we need to figure out the number that appears most often in the list. So we want to figure out what's the largest number essentially in this array, right? Because that'll be the number that appears most often. And we're going to say if there's ties, we just want the number that's the smaller number. So like if we have like, let's say this 4 over here, it appeared 5 times, and this 1 over here also appeared 5 times, we would just return 1. So how would we go through that? Well, I would say, now I'm going to need to loop, so I'm going to create a int I. I'm going to say for I is equal to 0, I is less than, the length of this is largest num, I plus plus. I'm going to get rid of that bracket. So all I want to do is I just want to find the largest number. So if I want to find the largest number, by the largest number I mean which of these indices has the highest value in it, right? So I'm going to need to keep track of what index so far has had the highest value and what that highest value previously was. I'm keeping like a running track of what this highest value is. So I'm also going to create max, and I'll say that's 0, and max index. And we're also going to say that's 0. So what I'm going to do is max is set to 0 and max index is set to 0. What I'm going to do is at each array, I'm going to check, is the number in here greater than max? Max is going to keep track of what the largest number we've seen so far. If it is, max is now this new number, and the max index is that index we've found. So if frequency sub I is greater than max, then I want to say max equals frequency sub I. So this is the new max, and max index equals I, right? Because I is our indices. Yes? If all the numbers are negative, something has gone wrong because we started everything at 0 and we're not decrementing anywhere. So ideally in this problem, nothing would be negative. So now at the end of this loop, we should have the largest number, right? Because this is just going to say, okay, max starts at 0. Is 0 greater than 0? No. So max is still 0. We get a 5. 5 is greater than max, so now the max is 5, and the max index is 1. And if we go through this array, it's never going to get overwritten. Assuming this is the end of the list, the end of the array, 5 isn't greater than max because we previously got this 5 from 1, so that means 1 is going to be our largest number. So all we would return here is we would just return max index. Oh, sorry. We would return max index because remember the indices up here are what the actual numbers in the list are. These values inside are just how many times they appeared. So max index is the number we're interested in because that's the largest number, or the one that appeared most frequently in our linked list. All right, so that's actually the last problem I have. Hopefully that helped you guys out in understanding a bunch of the core intro to C topics for your final exam. Real quick, I'm going to give you guys these surveys to fill out. If you guys could please go through these. They should be fairly quick. Here, I'll just hand them out. Go. If you guys have any questions also while you're filling out the surveys, we have some time now to go over these questions. And like I said, if you want to print out your own version of that and work through it again yourself, they should be up on the Study Union website. Oh, sorry, give me 2. Oh, sure, yes. Here, I'll just bring them to you, actually.
What number do you roll in?
The 41 there, so you do a 4 and then a 1. So do any of you guys have any questions? Any last minute questions about C? Yes.
Can you take pictures of the
Yeah, I've passed one back. Yeah.